Okay, so electric grid fundamentals, or what maybe I'm going to talk about a little bit more, is can the grid handle building, vehicle, and industrial electrification, which was, of course, a big topic at the end of the last session here. Okay, so next slide, please. So my short answer to that is yes. There's some caveats, right? Adequate planning is the key. Planning is a pretty big thing. We heard about planning for hooking up individual buildings. Newsflash, that was a big deal when I started at PG&E in 1981. So that's been an ongoing issue, and something that needs to be addressed. It's usually some credit to both sides of those things. The people, I think, colloquial look out and see the wire. Okay, PG&E, I'm ready. Run a wire. And it's more complicated than that, but that's been a problem for a long time. There's one thing Barry asked me to cover. There's a large number of policymaking bodies involved with this, right? They have different objectives, right? And they're not really at cross purposes, but they have different priorities. And so there needs to be maybe a higher level of cooperation and collaboration, and that's kind of, I think, what BayREN is about. To avoid some of these unintended consequences. So next slide, please. So let's take a quick look. CPUC, right? That jurisdiction over IOU rates and service rules, okay? That's who could say PG&E do a better job of hooking people up. And that's a pretty big, complicated question, and I'm sure it's been asked many times. But that would be the jurisdiction there. The California Energy Commission has changed a little bit over the years, but it has jurisdiction over power plant sightings. That has also come to me, or it meant originally, do we really need all these extra power plants? PG&E had plans to build 5 nukes the size of Diablo Canyon up and down the California coast. And a smart guy named David Goldstein, who's now at NRDC and has been for years, did a little study with Art Rosenfeld and determined that, if we just made refrigerators more efficient, we wouldn't have to do that. It's more complicated than that, but that was a big piece of it. Today's refrigerator uses 1/4 the energy of a 1970s refrigerator for the same size and all that. And it's a better machine, right? There's the independent system operator, CAISO. They operate the transmission system, which are the big wires out in the valley and so on, and that are high voltage. They, of course, have to do the planning and the infrastructure for that. And they have a competitive market for wholesale, that is wholesale energy. So that's a very active area, but it's quite narrow compared to the whole picture for energy. There's CARB, right? The California Air Resources Board. And they're the ones, their mission is public health, really, by making sure we keep the air as clean as possible. Then there's FERC, which is federal. And so then you've got this whole interface between state and federal, regulating interstate transmission of electricity and natural gas. They're the ones that are going to have to get, there's the wind, it's windy in places where people don't necessarily live. And so you have to get the energy from the solar farms and the wind down to the places where the energy is needed. And that we don't, in other words, have enough transmission, perhaps, in the United States. And then BayREN, cities, counties, CCAs, regional networks, all with missions that are not exactly the same as these other organizations. So the message here is to become as informed as possible about what these other agencies do. Okay, next slide. So I want to give some context on why I'm answering the question yes to can the grid handle it? And so I started working in 1981. Let's look at 2 decades from 1981 to the year 2000. And I think I dare say most of the people in the room, if they started working during those 2 decades, it was the very end of it. And probably a lot of you didn't start until after this, right? So that doesn't make me feel very good, by the way, but it does make me feel good to see a whole bunch of younger people coming in with a lot of imagination and a lot of drive to solve this problem. So 1981, California had 24 million people, 24.3. In 2000, there were 34 million. And that's a 40% increase. I just looked at what state is more or less equivalent to that. And Michigan right now has 10 million people. So you took basically, one way to look at this is you had the whole state of Michigan move to California in a period of 20 years. So all those people need energy, they need jobs, housing, roads, water, bridges, mass transit, they need all that stuff. And I would just say, if I look at that, what happened in those 2 decades compared to can we electrify things with the grid, I'd say, well, I don't know that that's an order of magnitude different type of a challenge looking forward than this would be, because this is pretty big. And there were numerous cases of the grid getting close to the limit. Obviously, the summer peaks. Summer peak for my religion for first 30 years or so of PG&E, or maybe 35, was noon to 6, noon to 6, noon to 6. Avoid power usage, noon to 6. And what is it now? 4 to 9, right. So pretty major change. And what's that about? That's about the renewables becoming less available and having to ramp up in that when the sun goes down. That's what that's about, right? So everything changes. Next slide. So I don't know a lot about the supply side compared to the demand side, because mostly I worked on the demand side. But there were numerous efforts, and it was an all of the above approach to keep the grid working and keep basically not have power blackouts. There were individual issues and so on, but generally, well, some of the things we did, there were something called the Large Interruptible Curtailable Rate Plan. I imagine there still is that, but the way it worked in the 80s was if we thought we were going to have a problem, well, the large industrial customers would sign up for this curtailable rate plan, and they'd agree to drop a certain amount of power, basically send everybody home if PG&E or needed it. And it was a statewide program, so I think the same thing applied down south. But we had this phone network of people, and if we got close and we needed the power, the general office people called the regional people. I was one of the regional people. I'd call the district people, and they would call the customers and say, time to turn off the power. And that worked, okay? You didn't get every single person or every single facility that signed up, but you got most of them. And those were very effective programs. Today, you do that very, very differently, of course. We had these time of use rate plans, mainly for commercial at that point. We had switches on swimming pools that were radio controlled, and also air conditioners. And so the customer would agree to do this. You put the radio control switch on the air conditioner, and if the relief is needed, their air conditioner went off for like 15 minutes or an hour. So I don't remember anymore. And the same thing with the swimming pool pumps. So there were the things like that were done. And of course, there's a giant investments in these efficiency programs, both transactional, in other words, rebates to customers under the CPUC jurisdiction, and then research, which was mainly under the Energy Commission. The year I started, PG&E recruited 200 engineers, both the year before I started and the year I started, to work on these commercial programs. So hundreds of engineers were brought in to work on these things. And of course, you had these building and appliance standards. The first building code went in 1978, and Charles Ely was instrumental in getting that to happen. I remember him coming in and talking about a new construction program. I go, well, how do we do that? The building, they're just going to plan and put the stuff in. I said, well, no, you make basically a model of the building. It's going to use this amount of energy, and you give a guy a rebate if he'll improve the efficiency of the new equipment. Oh, that's a good idea. That it seems obvious now, but that was really something at the time. Many efforts on the supply side, everything from Diablo Canyon to small power plants, cogeneration, things like that. Huge amounts of activity in that area. And of course, T&D upgrades, and that's ongoing. Next slide. Let's see. So where are we on time? Okay. So another thing Barry wanted me to talk about was kind of rate making 101 with the focus on what local government and regional organizations need maybe to keep in mind. Now the IOUs, Edison, Sempra, PG&E, that's 75 to 80% of the power or customers in the state. So pretty big. What do they want to do? They want to earn money, and the way they do that is from the infrastructure, not from the actual kilowatt hours and therms. However, the rates you pay are all based on the commodity, the kilowatt hours and the therms. That's not where the earnings are for the utility, and it's not the main cost either, the commodity. So the rates are based, the first thing, after about 3 years, I had this drilled into my head, PG&E. You start with a revenue requirement and a throughput or sales forecast. And it gets vastly more complex than this, but this is the fundamental thing. It starts with a revenue requirement. So when there's a rate case, Edison or PG&E or something goes to the CPUC and says, here's how much money, or here's how much money I need to serve this load, this number of kilowatt hours and therms. And then the CPUC says, you're nuts, it's way too high, blah, blah, blah. PG says, no. And they argue back and forth and negotiate, and they'll eventually come to a figure of a revenue requirement. So the revenue requirement then is the capital investment that the utility needs to make, its expenses, and its earnings, all right? The earnings are by far the smallest of those three things. The capital is what? The cost to build out and maintain the system, AKA pipes and wires. You've probably heard pipes and wires. The expenses would be your personnel costs, equipment, taxes, purchased energy, things like that. You know, when you buy a computer system or a desktop or something, that's an expense. The electric rate then, if you just make it this simple, it's the revenue requirement divided by the forecasted sales in kWhs. Now that's a pretty predictable number compared to most commodities. In other words, how many kilowatt hours am I going to sell is pretty well known compared to how many tomatoes you're going to sell, which is, you know, who knows? It's the weather, it's the supply, everything else. So you could probably going to be within 1 or 2% most of the time on those forecasts. Now there's dozens and dozens of rate schedules, but they all have a combination of variable and fixed costs. The bottom line is that the sum total from all of these rates, I'm going to get X amount of revenue from this rate, this rate, this rate, this rate, this rate. And that has to equal the revenue requirement. You design the rates to do that. All right. So, those sales can be modeled pretty accurately. How many therms are you going to sell? How many kilowatt hours? Okay, next slide, please. So the implications for an audience like this, what you're trying to do with this, and it's pretty much national for IOUs, is you want to collect your cost of service fairly in a public adjudicated way, and that includes a reasonable rate of return for the utility. So you're not going to, the forecast is never going to be perfect. So there's this concept of balancing accounts. So if the revenue requirement was, say, $1 billion, but the rates all led to the utility collecting 1.02 billion, what you do is over the coming years, you refund that 0.02 in the future rates. So it gets refunded, and if it's under collected, it gets added. So that's this concept of the balancing account, and that's how you square it up. The rates are always designed, the idea at least is to cause or effect cost minimization. So the top, say 1% of all kilowatt hours, or at least 20 times, maybe 50 times more than the average kilowatt hour. So you design the rate so that people don't use the kilowatt hours that they're making things get out of balance. They're really increasing cost. That's why you have these high peak charges. That's why you have time of use that is, I think some of the figures are close to 50 cents a kilowatt hour, things like that. And a really important thing for this group is if you have a subsidy or a discount to any given customer group, in other words, you deliberately say, I'm going to under collect the revenue requirement from this group, then the rest of the ratepayers have to make that up, right? That's how that works. You've got to make the revenue requirement. So if I under collect in one place, I've got to over collect somewhere else. So the revenue requirement then doesn't change because you want to give a discount to somebody. There's, of course, this is true for low income rates, economic development rates, and so on. I'm not arguing that we shouldn't do that. I'm just saying that does have to come back, and you still need to meet the revenue requirement. The same thing with NEM. The NEM rules have been very controversial there for rooftop solar. PG&E will say that's not worth very much, the rooftop solar, and the solar industry says, oh, yes, it is. That argument prevails and goes on. Okay, so next slide. So what's it mean? Something that doesn't get a lot of attention, I'd like to bring your attention to. Gas rates are collected volumetrically. In other words, you get a bill per therm. However, 5 minutes? Okay, we're good. The revenue requirement for gas rates is really dominated by infrastructure costs to a huge degree. And all you have to do is look up PG&E's G1 gas rate, the basic residential gas rate. And if when I did that the other day, the gas itself, which PG&E buys, is 75 cents a therm on average over the course of a year. It's way higher in the winter, it's way lower in the summer, but for the year, it's 75 cents a therm. For comparison, by the way, a therm is 100,000 BTUs, and a gallon of gasoline, I think, is about 130,000 BTUs. So gas is really cheap, right, compared to, say, gasoline. The transport, which basically means the infrastructure to deliver the gas to the home or the business, is $1.62 a therm. And that, again, that's an annual average. So what they are forecasting for 2023, and of course we're only halfway through, but the forecast is it would be $1.62, 68% of the bill. I'm sorry, in 2023 they expect it to be 75% of the bill. Now those figures are not like necessarily going to keep going up, but they're in that range of 70, 75%. So the really important thing is that infrastructure is cost, the revenue requirement is not going to change if we send less gas through the system, okay? You still have the revenue requirement. So what's that mean? Well, if you reduce the transport, say we meet these goals, reduced by 50% in 2030, then the rest of the people are going to have to pay way more for the natural gas. And that's the reason, it's a revenue requirement. Now this could be addressed in a lot of ways, but what's not going to change is you're going to have a revenue requirement to operate the wires well, mostly the pipes. Okay, that isn't going to change, and so people in local government just need to be aware of this, and maybe be working with the regulators and say, what are we going to do about this? And it's not going to be a matter of just give money. You know, it's going to have to be worked out in a lot more sophisticated way. So anyway, so the infrastructure and saving all this gas will have a huge impact on the total gas bill. What, 2 minutes or so? Okay, one more, I think. One more slide. Now, the good news is, as it was alluded to earlier, as you replace gas with electricity, you're going to increase the utilization rate of the power grid. And at least in a relative sense, that should be a downward driver on electric rates going forward. And I think that's what the CEC is forecasting, as was mentioned earlier. Over the last 40 or 50 years, the amount of grid that got used has steadily declined. A good reason for that, probably not the only one, but in 1960, 12% of the homes had air conditioning. Now, nationally, 91% of the homes have air conditioning. And so what that means is you're going to have a huge increase in peak, but it's really not that hot most of the time, okay? And so your utilization, instead of being like 75%, it's like 60%. So that's a bunch of grid that gets paid for and not used. So we're going to use more of it. That should be a downward driver on rates. So when you've got electrification and you do storage, especially with storage, you can really improve that utilization rate. And I think basically it's kind of an opposite impact of what I described for the gas system. So that's kind of the good news. Let's see, I think that's my last slide. Yes, there we go. How about that? Now I know I'm done. So with that, I think we're pretty much on time, and I'll pass it over.